Now to compare what we did with integrals in the last section with what we remember from calculus class. And so in the last section, we did integrals in this way. We took our function, and we had a and b. Tell you what, let's make this a little curvier. We took our function, and we had a and b, and we split it up into sections. And then in each section, we looked and we found the maximum value and we found the minimum value. And then we used the maximum and the minimum values to make our graph. So for example, we might use this for the maximum value and that for the maximum value of that one and that and that. And so we created an upper bound by making these what we called U, the upper sums. And then similarly, we would find the lower sums by using the lower value on each graph. So something like this looks like the lower sums on each of these graphs. And then what we did is we took the difference between the upper and the lower sums and showed that that comes to 0. Well, this is close, but not exactly the way we did it in calculus class. So way back in calculus class, the way you probably did it was we had some graph that looks like this. And we had A and B. And then we split it up into pieces. And then instead of finding the max and the minimum, we probably consistently chose a point. Like we might have chosen the midpoints every time. And that was called the midpoint rule. Or you might have chosen the left endpoints, and that was a left-hand sum, or the right endpoints, and that was a right-hand sum. But what's important is we took sample points. And we took sample points in here, and we gave those sample points names, and then we summed it up with the sample points. Well, this is a slightly different way of thinking about the integral, although if you're kind of sitting here going, well, shouldn't these two be the same thing? The answer is they should be the same thing. From a mathematician's perspective, however, we don't just assume they're the same thing. We go about trying to prove that these are actually two different ways to define the same thing and that they always give us the same results. So let's come here and define what we mean by a Riemann sum. So a Riemann sum of our function, and first we should know this is a function over a to b. So and as I said earlier, we always want our f to be bounded, and we're on ab. Then a Riemann sum with respect to a partition. With respect to some partition, so again, we still have partitions. Now, if we wanted to look even more like Calculus 1, we would make these partitions be very specific, right? And that is that the partitions would all have the same width, and you'd be b minus a over n, and then you would add them up across. But we're going to still keep this kind of arbitrary partition idea, and I think it's fine. So we have a Riemann sum with respect to that partition with sample points. And then those sample points we will call, I'll use t's, and we'll call those tj. And each tj is in the xj minus 1 xj interval. So given that picture that we had just a second ago, we would look at this, and this would have been T1, and this would have been T2, and T3, and T4. So this would have been X1 and X2, X0, X1, X2, X3, and X4. And then the T's are the points in the middle. They're the sample points that tell us how high to make our function. Okay, so then that series, we're going to denote it with S, F, P, T, J, and so this is just giving us F, F, P, T, J, and this is just going to be the sum of F evaluated at these sample points times delta X, J, where the delta is defined just as we did before. Okay, so this is how we define a Riemann sum, and we say the Riemann sums converge we say the Riemann sums converge to some integral I if, we say they converge to I as our partitions go to 0, so the norm of our partitions go to 0, if, and only if, no, not there exists, for all epsilon greater than 0, there exists some partition such that if we take a refinement such that every refinement of that partition and every set of sample points within that refinement, Tj and P. So given any refinement and sample points within that refinement tell us that S, F, P, Tj minus I is less than epsilon. So in other words, we find one partition that you can refine it as much as you want, and every single refinement you always get that you're within epsilon of I. Okay, so that's what we mean when we say the Riemann sums converge, and this is to be true for all partitions and all choices of Tj. And if this is true, then that I, the book likes to write I of F. I prefer to just write I. Then that I, we use the notation, is the limit, well, this is what's the book's notation, the limit as the norm of P goes to 0 of the sum as J goes from 1 to N of F of Tj delta J. Okay, so again, I hope this is kind of making sense, that this notation, this sum notation that we see right here, kind of looks like stuff that you did back in calculus class. The sum of F of the sample points times the deltas, this should be delta xj, times the width of each of the intervals, and then you add all of those up. And then you take the limit as the width of those intervals goes to 0, and that's what the limit as the norm of P goes to 0 is. Okay, so let's move on, and let's talk about proving the main theorem. I'm going to deviate a little bit from the book in the way I prove this, just because I thought the book made it a little complicated. Now, they did that in a couple ways to deal with some issues and to use kind of some of the notation they had. I'm going to brush over that a little bit and come up with kind of my own proof. And so, sorry about that. Come up with my own proof. So we'll do each of these first. So we'll go Riemann integrable implies. So we'll do this one first. We'll assume it's Riemann integrable and so show that sum converges. And then we'll go the opposite direction. We'll assume the sum converges and show that it's Riemann integrable. And in each case, we'll show that they have to equal the same thing. So in the first one, if f is Riemann integrable, then, okay. So we're gonna let f be Riemann integrable, and we will also let epsilon be greater than 0. Then because it's Riemann integrable, there must exist some delta such that if the norm of P is less than delta, then U FP minus L FP is less than epsilon. Okay, so that's precisely what that means. Now, I'm going to make an observation that, I think the book goes to a little bit of pain to make this observation, but it seems like it should be fairly obvious to me, and that is these U's are made up from the maximum values across the whole intervals. The F's, or the L's, are made up from the minimum, or maybe not even maximum, minimum, the sup and the nth values across the interval. And then the S that we had just a second ago is made up of just sample points within the interval. So I'll say because let's do the inf. The inf of f on the interval x j minus 1 xj is less than or equal to f of tj is less than or equal to the sup for any tj you choose, then we know that for any, because of that, then for any choice of p and tj such that the norm of p is less than delta, we get the following. So because those tj's have to be between the sup and the inf, we can choose any p smaller than this delta, and any norm of p, or any p as far as this norm is less than delta, and then any choices of tj's, and we must have that L is less than or equal to S is less than or equal to U. And then you can already see right now that if it converges, then that L and that U are converging to 0, are converging to whatever that value is. But I'm just going to subtract the integral of a to b off of each of these. And then I'll go then. Yeah, I was going to subtract the integral off of each of these. Maybe I should be a little bit more careful and notice that there's an implication here that I kind of don't really want to go too into detail for. But it's that if this is the case, then I know that that my integral must be somewhere in between these two, right? That what I defined as the integral from a to b of f of x dx, which is the inf of all these u's and the sup of all these l's, it must be somewhere between u and L, right? So that must be true for those things. So what I'm going to do is I'm just going to come here and subtract the integral off of each of these. So L minus the integral from a to b of f of x dx is less than or equal to S minus the integral from a to b. And sorry, I'm being a little bit lazy. I just don't want to fill up the whole page with things that you know what they are. Is less than or equal to U minus the integral from a to b of f of x dx. So we just subtracted all those integrals. But now what I see is that this piece over here must be less than epsilon, because u minus L is less than epsilon, and this is in between the two. And this piece over here must be less than epsilon for the same reason. Oh, look at that. Hey, I wrote my u's and my L's backwards just a moment ago. I wonder if any of you noticed that. If so, give yourself a pat on the back for noticing that I wrote things backwards. And so, okay, so therefore, what I'll notice is that negative epsilon is less than or equal to S minus that integral of f of x dx is less than or equal to positive epsilon. So that gives me my final result, that S minus the integral from a to b of f of x dx is less than epsilon. And this is true for an arbitrary epsilon, so that means that sum must converge, and that sum must equal the integral value that we had before. Okay, so that tells us this direction, that if it's Riemann integral, then the sum converges. So going back to where we were just a moment ago, thinking about this, that tells us that if this problem, the first problem, works, then the second problem works as well. Now we just need to go the other direction and show that, well, if these sample points converges, then that means we also have upper and lower limits that converge. So we're really just taking these two definitions and trying to show that they're the same definition. Okay, so let's do the backwards implication, and let's assume that limit converges. Assume, and here I'll be even super lazier than normal, and I'm going to assume that limit converges, and then say, well, what does that mean? And then I'm also going to let epsilon be greater than 0. Okay, so assume that converges, then there exists some partition, p epsilon, such that every refinement of p epsilon implies every refinement at p epsilon and every choice of tj gives that s f p tj minus our integral value is less than, and I'm going to do epsilon over 4 because I'm going to be gluing a whole bunch of these epsilons together at the end of the proof. Now all I'm going to do is I'm going to notice that since, and I'll just make a quick observation about soups that we knew earlier. I'm going to say since well, so first I'm going to define m sub j to be the soup of f xj minus 1 xj. So I'm just going to take m will just be the soup of all the values. And then since it's a soup, I know something. I know that there exists some f value, and I'll say there exists some tj, such that f of tj is greater than mj minus epsilon over 4. So in other words, if I have a soup value, I can back off just a little bit from that soup value, epsilon over 4, and then I can find some point in there. And that's what it means to be a soup value, right? That it's an upper bound. So if I pick a number smaller than that upper bound, there exist things in that range. Okay, well that's actually really nice. Oh wait, I didn't want. Yeah, let's go 4. Epsilon over 4, and then I also want b minus a on here because I'm going to do like I did on the proof in the last video where I have a lot of telescoping and the b minus a cancel each other out. Okay, so now all I'm going to do is I'm going to come here and ask, well, what if I choose these tj values, because I know that every tj value gives me less than epsilon over 4. What if I chose these tj values? Then what would happen? Well, then I know that u minus s. Tell you what, let's write them out. U of fp minus s fp using these tj values I chose just a second ago equals the sum. And now notice this part, the u part, gives me the mj's every time, and the s part gives me the ftj's every time, and so it ends up being that times delta xj. Well, this is now less than the sum. Well, each one of these are less than epsilon over 4 b minus a times delta xj. But now this is a constant. If I add all the delta xj's up over here, I get epsilon over 4 b minus a times all those delta xj's give me b minus a. So therefore, I get that this equals epsilon over 4. And then I could do the same thing for the nth, and similarly, if I take, let's do s minus the nth, or L, s minus L of fp is also going to be less than epsilon over 4. Okay, so now we're ready to start gluing stuff together. And the way I'm going to glue stuff together is this. Let me erase some things here. Maybe I'll just clear the whole page. So let's erase some things here. So the way, again, we're going this direction. So the way that I'm going to glue some stuff together is I'm going to notice, well, therefore, if I take u minus my I value, which is whatever that integral that came from the sum converging, well, this must be less than or equal to u minus that sum value plus the sum value minus I. But this is equal to epsilon over 4 plus epsilon over 4, which is epsilon over 2. So my u is with epsilon over 2 of that integral value that comes from that summing, because I know u is very close to s, and then s is very close to that integral value. Okay, and also I can do the same thing for L. So let's go I minus L is less than or equal to I minus L plus S minus I, and that is epsilon over 4 plus epsilon over 4, which is epsilon over 2. And then finally, I can compare my U and my I together. And so I can compare my U and my L together, because this is U minus L plus L minus I. And that is epsilon over 2 plus epsilon over 2 is epsilon. Oh, I guess these should have all been less thans here, right? Yeah. So, and then that piece is now less than epsilon. So what did I do really? I said we know this converges to some number I, and so once we have that fixed number I can compare U to that to the sum take with sample points, and then compare those sample points to I. So that lets me compare my U to my I value. Similarly, my L is close to my I value. So then L and U must be very close to each other. They must be within epsilon from each other. So therefore, F is Riemann integrable. And how do we know that that they give us the same value? Well, we could, in some ways, repeat the past theorem again. So F is Riemann integrable, so the limit has to converge to that integral value. But let's not worry about it. Let's recognize the big conclusion. The big conclusion is that these two ways of thinking about the problem are actually the same. So if you want to think about the problem as taking upper estimates and lower estimates and then letting those upper and lowers converge to each other, that's great. If you want to think about it as taking sample points and then letting your partitions, the size of your partitions go to 0, that's great. You actually get the exact same result either way that you choose to approach the problem. Okay. Why would we want two ways to approach the integral? Well, other than the fact that it's fun and it's kind of a way of us teachers torturing you students. No, that's not the reason why. And in fact, the ways that we did it, there are subtle differences. And probably if you read a dozen textbooks, you would find multiple different variations of the way different textbooks treat setting up these definitions. They're all the same in concept, but often the notation or just little details about how they set things up vary. But one reason you might want to have two ways of talking about integrals is some proofs are more conducive to one method than the other. So for example, if I want to prove that the integral from a to b of f plus g of x dx equals the integral from a to b of f of x dx plus the integral from a to b of g of x dx. How might I want to do that? Well, I might want to do that by using sums with points, because that kind of feels like a sequence. So this definition that we're doing right now feels kind of like a sequence definition. And what I would notice is I would go that sum of the f of tj's delta x's minus the integral of f of x dx is less than epsilon over 2. So that's what it means for that integral to exist. Similarly, the sum... Now, by the way, you all recognize that I'm leaving out like most of the details of this proof, including I didn't tell you what we know about the functions, and mostly we know that they are integrable and they converge to these integrals right here. And then all the other details are that, well, once we know they're integral, then we know there exists partitions that do these things. Okay, but anyway, once we pick that partition that does all these things, then actually, probably the book should have been a little bit more careful, because we know that there's one partition that makes f less than epsilon over 2. There's a different partition that makes g less than epsilon over 2, and then they probably should have talked about the union of the two partitions, a refinement of both of them. And then that gives both of these. And then if you refine that, then you're always within the same state. Okay, so this difference less than f, so therefore the sum of f, oh, sorry, this should have been a g here, shouldn't it? Okay, This should have been a g of tj's. We probably, g of tj's, well, this should be f plus g, the sum of f of, oh, the sum of f of tj plus g of tj with our delta x's. And then we just get that minus these two sums is less than epsilon. So, and then how would we do that? Well, we would split these sums up and then do the triangle inequality. So I'm not going to work out the details, but you can see how this is a proof that really kind of lends itself to using the techniques of sums, because sums easily factor and things like that as well. By the way, another proof that's right along these same lines is that the integral, if you put some constant, the book uses alpha f of x dx, then constants come out of the integral. And this is something that you know from calculus class, that we can factor out constants. A proof that was done earlier in the previous section that I skipped is that what if you had the integral of just some constant alpha dx, and that ends up being alpha times b minus a, and it turns out that in fact either method works just fine for this one. But this is a good thing to note, how to do the integral of an interval. Okay, a couple other theorems in this section that we'll get to, and maybe I might prove a few of them. One of them is the comparison theorem. And again, let's not go through all the gritty details of the comparison theorem, but it basically just says this: if f of x is less than or equal to g of x for all x in AB, assuming that f and g are both integrable functions, then the integral of f of x is less than or equal to the integral of g of x dx. Okay, so there we go. So we've got if f is less than g, then the integral of f is less than the integral of g, and that makes complete sense. And so so how are we gonna prove this? Well, this one is actually one that lends itself a little bit more to using the first definition one with the u's and the p's. And the reason is we know that that this integral from a to b of f of x has to always be less than or equal to the u's of the f of x's for any partition. But notice if f's are always lower than g's on that interval, then those u's of that partition, then it also has to be less than or equal to the g's in that partition. Well, then what we can do is we can say, okay, well, we know this works for every partition. We take basically a lim sup over those things, and right, we're kind of like taking the limit we're taking the sup. Or the inf, sorry, limit. We're taking the inf of all these sups over this partition. Maybe I shouldn't call a limit. That's not quite a fair characterization. But we're taking the inf of all these upper sums, and so then that means this integral eventually has to be less than this integral. Okay, so that's kind of at the heart of how we might prove this theorem. And notice that it really lends itself to this upper and lower sum, because you know you have an upper sum with the g's and f's, and you know the relationship between those because we know the relationship between g and f. And so similarly, you can use the lower sums to show that that it must be bigger than the lowers, and so then the integral has to be right there. Oh, wait. Yeah, you don't worry about the lowers. Okay. You just get that it's less than this. Okay, one other conclusion from this theorem, which is nice, which you see people talk about a lot, is notice what would happen. What happens if we let m equal the minimum value, or the inf of f? I guess it's actually a minimum value. No, we don't know that it's continuous. So if we let m be the inf of f on that interval AB, then what do we notice? Well, then that means that means that m, the integral of m dx is less than or equal to the integral of m f of x dx over that interval. And so that means m times b minus a is less than or equal to that integral from a to b of f of x dx. And that ends up kind of being a nice result. Similarly, if we did the same thing with a capital M equal to the sup, then this is less than or equal to capital M of b minus a. And you see how there's all sorts of nice things you could do. You could divide by b minus a or things like that. But this ends up being a really nice inequality for a lot of different problems, giving you some way of bounding f. So once you know f is bounded between a lower and an upper bound, then you just multiply it by the width of the interval, and you're in business there. Okay, one theorem that I think is a really nice one is this theorem that compares integrals with their absolute value. And it says this. It says, what happens if we take the absolute value of the integral of a to b of f of x dx? Well, this happens to be less than or equal to the integral from a to b of the absolute value of f of x dx. And as you see this, you should probably think a little bit about like the triangle inequality. So notice we have the triangle inequality. The absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. And so if you think of an integral as like a sum, well, at least when you approximate it, it's a sum, then you're basically using this triangle inequality, but with many, many pieces to get this result. And so this, like I said, this is in some ways a triangle inequality result. We're going to do it without the triangle inequality, although I think we could. So let's start with just a quick observation, right? And that is that if I let mj be the sup of f, and then I compare that, well, that should actually always be less than or equal to the sup of the absolute value of f. And we can see why this should be the case. That's because, which we'll call mj absolute value of f. And tell you what, we'll call this one mj of little f. Okay, and this should be pretty obvious. This is just because all of our f's are always less than or equal to our absolute values, right? And similarly, if I deal with infs, then I know that little mj is always greater than little mj of f is always greater than, oh, wait. No, little mj of f is also always less than little mj of the absolute value of f. Okay, so let's see. So what the book wants to do is to subtract these and get a nice result. Okay. Yeah, so that means that, so what the book wants to do is well, what if I take mjf and subtract little mjf from it? Can I show that this is, in fact, greater than what happens when I do it with the absolute values? And, you know, it's kind of a bunch of tediousness going back and forth about maximum and minimum values. You know, when I first started the problem, I thought it was going to be obvious. I thought we were just going to set these up, set this minus this is less than this, and this is less than this, and then subtract them. But it turns out that you can't do that, right? Because if you just subtract, you're not always guaranteed that things come out that way. But this ends up being a true inequality, and so we will hold on to this equality and not go through the details of it, and instead just kind of notice how once you have this inequality, you have the result. Okay, so the result is let epsilon be greater than 0, and choose a partition such that, and P be a partition such that U of F P minus L of FP is less than epsilon. That's what it means for the F's to converge. Then what we know, then well, that means that that if we take our absolute values, then we're lower than our non-absolute values. Then U of absolute value of F P minus L of absolute value of F P is less than or equal to that U of non-absolute value of F P minus L of non-absolute value of F P, which is less than epsilon. And I guess I didn't really need all of my my absolute values on the U's and L's there, because we know which one's larger. And so this implies that the absolute value of F is also integrable. Now, again, I cheated because I used this inequality that I didn't really want to prove, because it's a little tedious and I didn't want to go through all the details of it. But you guys can read it if you want on your own time. Okay, but then once I know this, then I know one more thing, and that is that I know negative, the absolute value of f of x, is always less than or equal to f of x, is always less than or equal to positive, the absolute value of f of x. So that just means we can use the comparison theorem to show that negative, the integral of absolute value of f of x dx is less than or equal to the integral of f of x dx is less than or equal to the integral of positive, the absolute value of f of x dx. And then now we see that it works out really nicely because we just move that to the other side. This is exactly what it means for the integral of f of x dx to be less than or equal to the integral of the absolute value of f of x dx. Oh, I guess I left off all my a's and b's. Okay, you all know that they're there. Okay. Okay, well, there we go. I feel like that was a lot of talking, and I'm ready to move on to the mean value theorem for integrals. It turns out that there are two of them, and we will talk about both of them. And I'll talk about the proof of the first one, but not the second one. Maybe we can talk about both proofs if we want. But tell you what, yeah, let's talk about both proofs if we want. But what does the mean value theorem for integrals basically say? It says that if g is a function that's greater than 0, so g is an always positive function, and f and g are integrable, then the integral from a to b of f of x times g of x dx is equal to c. Oh, I should have said, then there exists some c in a and b. Oh, no, I shouldn't say a and b. Oh, okay, I need to write. Man, sorry. I've been sitting here for a long time talking, and just as you're sitting there for a long time listening, we're going to let them be integral. We'll let m equal the inf of f of a of b. We're talking about the f function here, and we'll let capital M be the sup of f of a and b. Then there exists a c somewhere in between that inf and that sup, such that f of x equals c times the integral from a to b of g of x dx. Okay, by the way, usually when you see this used in practice, what we'll do is we'll let g of x be a constant. So we'll let g of x equal just the constant 1, and then what you see is that the integral from a to b of f of x dx is equal to c times b minus a. So So this is often how it's used in practice when g of x is equal to 1. But we'll do it a little bit. We do it a little bit more general because then it's a little more useful. And by the way, if f is continuous, then that c can be replaced with a value of the function itself. So we can replace these c's with the values of the function itself. Okay, well, the book kind of had its own way of going about the problem. What I thought might be kind of nice would be just to recognize one quick thing, and I thought it might be nice to kind of think about this in terms of the intermediate value theorems. It kind of feels like an intermediate value theorem, or I guess mean value theorem type of problem. And I'm a little uncertain. Okay, so we'll go through this and we'll see if we can find out what we think about it. So what I'm going to do is I'm going to let a capital F function be the integral from a to b of f of x g of x dx minus, let's let capital be a function, we'll let t be the variable, minus t times the integral from a to b of g of x dx. And then what I'll try to notice a few things. If t is, say, the minimum value, right? So capital F of whatever that minimum value is, so capital F g of x minus that obviously must be greater than or equal to 0, because if you multiply by the minimum value of f, you always get something less, because that t could be inside of here, right? And this is because of the comparison theorem. The comparison theorem where we're comparing f of x, g of x to the minimum value times g of x. Okay. Now notice it is important that g is always positive, because this comparison might not be true if g isn't always positive. Okay. So notice that the minimum value is always less than 0. Now similarly, f of the sup, or the maximum value, must be less than or equal to 0 by the same comparison theorem. So therefore, we get that f of little m is greater than 0, f of m is greater than 0. So by the intermediate value theorem, there exists a c in the interval m capital M, such that f of c equals 0. And notice if that c equals 0, that's exactly the c that we're looking for. So I kind of like using this function and relating it back to the intermediate value theorem. This is slightly different than what the book did, but again, I thought this looked nice, so I was kind of I was okay with this. You can agree. I mean, maybe I did something that would upset someone who's really nitpicking the details. But I feel like even if you're nitpicking the details, this gets at the gist of the theorem and why it's going to work. Okay. One more thing to talk about, and then I'll introduce the second mean value theorem, and we'll kind of talk about it and why it should be true. The last thing to talk about is this function right here, which is going to show up in the next section where we talk about the fundamental theorem of calculus. And this is what we call an accumulation function. And you probably remember these from calculus or from somewhere else, but it could be they were never your friend before. But I hope that by the end of this semester, they will be your friend. And what are we really talking about? Well, back in a calculus way of thinking about it, we have some starting point a, and then some other point x, and we have our function, and we're taking the area from a to x, and what we're doing is we're letting x increase. So we go from x to there, and then as x increases, the area is increasing, and capital F is how much area there is for each x. So if this is x1, then as you get to x2, you have even more area, and so f of x2 would be bigger than f of x1, assuming little f is positive. Okay, so this is what we call accumulation function, because you can imagine as this line moves to the right, you're accumulating area behind it. Again, if your function is below the axis, you're accumulating negative area behind it. But okay, so what do we want to prove? We want to prove that this accumulation function is in fact a continuous function. And then once we do that, we're going to be able to do things with that, both next time when we do the fundamental theorem of calculus, and in a moment when we talk about the mean value theorem for integrals. The second version of the mean value theorem for integrals. Okay, so so how are we going to prove that this is continuous? Man, I've been going a long time. Okay, so at the heart of why this is continuous is this picture right here. And that is, if I go from a to x, if I go from a to x1, well, if I let x2 be just barely bigger than x1, then what do we notice? Well, we notice that that area right there is really small, and we can let that area be small enough so that when these two are within delta of each other, this area is less than epsilon. And so that's kind of the big idea of making it continuous. And so what the book does is, well, they go through some details that I'm not too crazy about. Again, you guys are learning. I don't like being really too obsessed with all these details, but okay, let's go for this. So let m, so f is integrable. Let m be a real number such that f of t is less than or equal to m for all t in between this interval a to b. Then we'll let delta equal epsilon divided by that capital M. And then what we know is that if we let x minus x naught be less than delta, then we get the following inequality. Capital F of x minus capital F of x naught is equal to the integral from a to x of f of t dt minus the integral from a to x naught of f of t dt. Well, we actually know that these two integrals, and I guess this was a theorem that I skipped earlier, but we know that if you go from a to x and then a to x naught, that the difference is that integral between, because the integrals over areas add as long as they share endpoints with each other. Okay, so I know that this is equal to the integral from x to x naught of f of t dt, but this is less than or equal to the integral from x to x naught of the magnitude of f of t dt. But that magnitude is bounded because we chose an upper bound, so the m is an upper bound for it. So this is less than or equal to the integral from x to x naught of m times of m dt, which is equal to m times delta, which, because delta is the distance between x and x naught, but now this is, since delta is epsilon over m, this is epsilon. Okay, so that's at the heart. So that's why this function right here ends up being continuous, and that's kind of an important function to be continuous as we go through the rest of the semester. All right. So this brings us to the second version of the mean value theorem. And the first version of the mean value theorem involved the integral of the whole region. And so in some ways, if I think about the first version, we have something like this. We have our smallest value, little m, and our biggest value, capital M. And it's like we're comparing our function to those two in a way. And so we're finding some value in the middle where some value in the middle here. I didn't mean to do that. We're finding some value in the middle here, c, where when you take that integral you get the same thing as the integral of this big region. So we get the integral of this blue region here is the same as the integral of the black region. And so this was what it was when I let g of x equal just that constant 1. So this was at the heart of what was going on with that one. Well, this one, what we're going to do is we're going to change it up a little bit. And this one, we're going to integrate part of the way and then integrate the rest of the way. So that may not have made sense because I'm getting tired. Sorry about that. Of f of x gx dx equals, we're going to use that same minimum and maximum notation. Of g of x dx. And importantly, again, if g of x is equal to 1, which is where these become useful, although they're useful in other situations as well, but if g of x is equal to 1, then we get the integral from a to b of f of x dx equals m times c minus a plus capital M times b minus c. And so that kind of gives you a little bit of that result. By the way, I should have probably told you that C is now between A and B instead of C being between capital M and M. So C is between A and B. Okay, how are we going to prove this one? Let's prove it, and then I'll talk a little bit more about how to think about the difference between the two mean value theorems. So the way we prove this one is we just set up a function, and we just set our function to look like this. Capital F of x is little m times the integral from a to x of g of t dt plus capital M times the integral from x to b of g of d dt. And then what we see is that, well, this thing is, if we do, if we let, so what we see is that if we let f of a is just the maximum value, is just m times the integral from x to b of g of t, which is obviously dt, which is obviously bigger than that integral of f of x g of x dx. So what we're doing is, if it equals to a, then we're looking at just the second half, but we're comparing it to our original value. So in this case, this side must be much larger. However, if we look at f of b, you'll notice that we get the opposite result. So if I look at capital F of b, then that's little m from a to x of g of t dt, and so that one is obviously less than the integral from a to b of f of x g of x dx. Okay, putting those two together, I know from the previous theorem that f is a continuous function, and I know that capital F of a is greater than the integral from a to b of f of x g of x dx is greater than capital F of b, and so the intermediate value theorem tells me there must exist a c such that f of c equals that integral right there. So the intermediate value theorem, again, with this function, which I now know is continuous by the theorem we did just a minute ago, because we know these functions that have variables in the integrand are continuous functions. Okay, so this is what we call the second mean value theorem. Again, I encourage you to kind of keep going and looking in the book. And let me just for a quick moment point out the difference between the two. So for both of these, let's assume g of x is equal to the constant 1. Kind of ask, well, what's the difference between them? Well, the first one, we have a picture that looks something like this, and I'll take my function looking like that. I'll tell you what, let's make our function look something like that. from A to B. And then on the first one, what we're doing is we're finding a value. We're comparing this area right here. Right? We're comparing that area. And what we're doing is we're finding a value in the middle such that if I take the area of that rectangle, I get the same amount. So I'm looking for some value where like the amount that we're under over here on the left and the amount that we're over on the right and the amount we're over here on the left kind of matches up each other, and those end up giving us the same value. So that's that first mean value theorem. And so here our C is like the height. Our C is like how high do we want our rectangle to be. Well, our second mean value theorem, we're thinking about the problem a little bit differently. So the second mean value theorem, I'll try to draw, there we go. That's not quite the same function, but we can deal with it. We have A and B. And our second mean value theorem, well, what I'm doing is I'm taking, again, the same area, but this time I'm actually going to compare my minimum value, which is right here, with my maximum value, which is right here. And I'm not going to make a rectangle, I'm going to actually make two. So I'm going to divide it somewhere in the middle. Somewhere like right here will be our C. And then what I'll do is I'll draw that rectangle, and then I'll draw a rectangle. So the C tells me where to divide our two rectangles so that the two sides add together to equal the entire amount. So in the first one, our C is telling us how high we want it to be in terms of the y-axis. Here, our C is telling us how far to the left and right do we want to go to give us that value right there that splits our area up into two rectangles. That's the same as the original area. Okay, I hope that makes a little bit of sense. I feel like I've rambled for a long time. I'm sorry these videos are so long, but we still have one more to go.